This video covers section 3.1, quadratic functions and models. A quadratic function is a polynomial function of degree 2, so the form is given below, f of x equals ax squared plus bx plus c. A, of course, can't be 0, or we'll wipe out that x squared term and it will be a linear function instead. You should have some familiarity with quadratic functions already. Here are a couple of examples. There's a quadratic function. Do you remember what the graph of a quadratic function looks like? We're going to review what the graph looks like and look at some new ways to think about it. But you should remember it looks like a parabola. That's a shape that looks either like this or like this. This sideways parabola isn't going to pass our vertical line test, so that's not a function. We're not looking at those, just parabolas that open directly up and directly down. We can write a quadratic equation in lots of different forms. We just saw the form ax squared plus bx plus c in the previous slide. Here's another useful form known as the standard form in our textbook. It's also sometimes known as the vertex form, and we'll see why. If you remember, the vertex of a parabola is that very highest middle point or the lowest middle point, depending if it opens up or down. Standard form is f of x equals a times x minus h squared plus k. Let me see if I can show you through an example why this form is particularly useful. Let's try sketching a graph of this function, 1/2 times x minus 1 squared minus 2. And the cool thing about this form is I can see how this compares to the graph of x squared. This is going to take my graph of x squared and shift it to the right one, down 2, and this is going to cause a vertical shrink by that factor of 1/2. So if we think about our regular x squared function, which is very familiar to us, this parabola, all I need to do is shift this to the right one, down 2, and shrink it by 1/2. So if I think about this point, which we know as the vertex, I want to shift that vertex to the right one and down 2. So in order to graph the function we're looking for, instead of a vertex at 0, 0, it's going to be to the right one and down 2. So here's my vertex. It's still going to open up. It would only open down if we had a negative here, right? It's still going to open up, but it's going to be vertically squashed. It's going to look similar but be a little bit wider. New vertex here at 1, negative 2. So this is just a rough graph, but I wanted to give you an idea of why this form is useful, because we can see what those transformations are. And in particular, we can really figure out what that vertex is pretty easily. Let's just note a couple of things. These values, the shift to the right or left and a shift up or down, are going to help us figure out what that vertex is. And this tells me that it shrinks, but also because it's positive, it tells me that our parabola opens up. If it's negative, it would flip it upside down, do a reflection vertically and open down. When we have a quadratic function in standard form, that's a times x minus h squared plus k, we can express it that way by completing the square. Hold on to that thought for a minute. We'll do that soon, or think about how that works, how we go back and forth between these forms. But in standard form, I know that the graph is a parabola with vertex hk. I have a minus sign in here in the form. That would mean shifting to the right if h is positive, the left if h is negative. That's going to give us our vertex at hk. Opens up if our a value is positive, that's right here, and down if our a value is negative. Let's think about that with an example. I've got a quadratic equation here in my standard form or my vertex form. I want to know, what is the vertex? Well, x squared, my parabola y equals x squared, has a vertex at 0, 0. That vertex is being shifted to the left 9 units and up 17 units. So that's going to put my vertex at negative 9, again, because this shifts to the left, 17. Does the function have a maximum value or a minimum value, and what is it? Well, because this is positive, I know that the shape of this is a parabola opening up. So I would say this has a minimum value, And in fact, that minimum value is just the y value of the vertex. So I would say this has a minimum value, and that minimum value is 17. What are the domain and range? Well, all my quadratic functions have a domain of all real numbers. There's a symbol for all real numbers, or the interval from -infinity to infinity. I could plug anything in here, add 9 to it, square it, multiply it by 2, and add 17. My range, though, isn't all real numbers. If we think about what the graph looks like a little bit again, I know that my range is starting at 17 and going up. So my range is 17, include 17, that's my minimum value, up to infinity. Here's one for you to try for participation points. Find the vertex, a minimum or maximum value, and the domain and range on this. And you can answer all three of these for those participation points. There'll be another opportunity for more in a little bit. Let's talk about completing the square. So it said we could change between that form ax squared plus bx plus c and our standard form by completing the square. So I'm going to try that here. Here I have a function in our form ax squared plus bx plus c. How do I write it this way? If I can write it this way, then I can easily tell what the vertex is, if I've got a minimum or a maximum, all of that good stuff. Let's see if we can get some reminders about completing the square. We reviewed completing the square when we were looking at solving quadratic equations. Now I've got this expression not equal to 0, but equal to f of x because I have an entire quadratic function. I can complete the square in the same way. I just have to make sure this f of x is in here instead of a 0. Remember, to complete the square, first I need to figure out what I need to add to both sides to make this a perfect square polynomial. And it's not 3 because it's not a perfect square polynomial as is. Let me just get this 3 over to the other side. This is the way I like to do it, so I don't have to worry about that 3 for a moment. And since I didn't have a 0 or anything over here, I had f of x, it's just f of x plus 3. And now if you remember this piece, in order to figure out that magic number we add to both sides, I need to look at this coefficient. I need to take half of it and square it. So this is going to be 25. I can see that if I add 25 on this right-hand side, this is indeed a perfect square trinomial. This is x plus 5 squared. In order to make this equivalent, well, I added 25 over here, so I also have to add 25 on the left-hand side. So this is going to become f of x plus 3 plus 25, or f of x plus 28. I'm almost to standard form. Let's just subtract this 28 back to the other side. So in standard form, I've got f of x equals x plus 5 squared minus 28. I'm not going to dwell too long on this steps for completing the square in this way. What I'd like to go ahead and do, although certainly practice this, I'd like to complete the square for our generic function f of x equals ax squared plus bx plus c. Because if I do that, we can determine a relationship between the two forms in general. And if I have that, I can perhaps even come up with a formula for the vertex. What does that h and k become when I translate it directly from ax squared plus bx plus c? So this is going to be kind of algebra heavy, but if we can do this, maybe we can come up with a nice shortcut, a formula to finding that vertex and writing this in standard form. Let's grab f of x equals ax squared plus bx plus c. I'm going to complete the square on this guy in general. It's going to have a lot of a's and b's and c's floating around, but I think we can do it. The previous one didn't have a coefficient other than 1 on x squared. This last example that we did, it was just x squared plus 10x minus 3. It gets a little messier to try to complete the square if we have a coefficient on x squared other than 1, but let me give you a way to kind of cheat and get around that. Let's just divide that a out. So I have to divide everything on both sides by a. But if I do that, I won't have to worry about a coefficient on x squared over here. The not so great thing is it does create some fractions for me to deal with, but let's see if we can handle this. Now remember, I would like to subtract this c over a from both sides because that's not what gives me that perfect square trinomial. And then I can look at what I need to add to both sides to get that perfect square. So I subtracted that c over a from both sides and it looks like this. And now we need to find that magic number. Remember, it was to take this b over a and take half of it and then square it. So it looks like this is going to be b over 2a squared or b squared over 4a squared. This is the number that I need to add to both sides to create that perfect square. So I'm going to add b squared over 4a squared to both sides. That gives me f of x over a minus c over a plus b squared over 4a squared is x squared plus b over a x plus b squared over 4a squared. And now if I factor, this side should be a perfect square trinomial. I can see if I multiply this out, I'm going to get x squared plus b over ax plus b squared over 4a squared. If you don't believe it, give it a try. On my left-hand side over here, I've got f of x over a minus c over a plus b squared over 4a squared. If I really want to get it in this form, well, so far I know what my h is, don't I? But I need to get f of x by itself again. So let me add these two terms back onto the other side. If I add those to the other side, I've got f of x over a equals x plus b over 2a squared plus c over a minus b squared over 4a squared. And then one more step to get f of x by itself. Let me multiply both sides by a here. Okay, so what have we learned from all this? Well, let me clear the rest out and just focus on what we've got here. Well, this is telling me that my value for h, or the x value of my vertex, is negative b over 2a, right? Negative because I'm subtracting in the form when I write it this way. Or note this is a shift to the left if b over 2a is positive, so it's going to bring me to negative b over 2a. And my k value is all of this stuff, c minus b squared over 4a. Well, a formula for the vertex, well, my h value is negative b over 2a. My k value is this kind of messy piece, although you know what would make this easier? I could also find this messy piece. I can find any y value that goes with an x value by just plugging this back into the function. So it might even be easier if we just go with this, easier to remember. This gives me a formula to always find my vertex. If I start with something in this ax squared plus bx plus c form, I know that if I complete the square and put it in vertex or standard form, my vertex ends up being negative b over 2a, and the y value, easiest way to find it, just plug it back in, f of negative b over 2a. This is called a vertex formula. I would probably commit this one to memory. Let's just see how this formula works. I'd like to write this equation in standard form, and I'd like to find the maximum or minimum, which is just the y value of the vertex. Instead of completing the square to write it in standard form, I'd like to use the fact that my vertex is going to be negative b over 2a, f of negative b over 2a. Note that my value of a here is just 1. And in fact, a in both forms is the same exact value. We ended up with the same a out here in front as what we started with. So a is going to be 1 in this case. Let's go ahead and calculate the vertex by finding negative b over 2a. That's the opposite of negative 6, so positive 6, over 2 times a is 1. This is going to be 3. So I know that the value of h, or the x-coordinate of my vertex, is 3. To find the y value of my vertex, I can take f of negative b over 2a. In this case, this is f of 3. So this is 3 squared minus 6 times 3 plus 10. I could also use that big expression with b squared over 4a, all that stuff, plus c, but this is just a little bit easier and we'll find it in the same way. This is 9 minus 18 plus 10. Negative 9 plus 10 is 1. So this is my k value of my vertex. That means that instead of completing the square here, I could just jump in and write this in the form a times x minus h squared plus k, knowing that a is 1, h is 3, and k is 1. Here's my equation in standard form. The minimum or maximum value, I've got that also. It is a minimum value because this is a parabola opening up. I know that because a is positive. And the y-coordinate of my vertex is going to give me that minimum value of 1. I'd like you to try that with this example. Write it in standard form and find the maximum or minimum value. Here's just a summary of that vertex formula, a little bit more cleanly stated. The minimum or maximum occurs at x equals negative b over 2a. If a is positive, it's a minimum because that's a parabola opening up, and the minimum value is that y value associated with it. If a is negative, our parabola opens down, so it's a maximum value, and we find it again by calculating the y value when x is negative b over 2a. One more example for participation points. Find the vertex and express the equation in standard form. Give that a try. Express it in standard form, so we'll get some more practice with that. Find the x and y intercepts and sketch a graph. All right, let's give this a try. First, let's express it in standard form. So that's f of x equals a times x minus h squared plus k. I could complete the square, but what we just saw was that it's a little bit faster if we use our vertex formula to find h and k. So negative b over 2a in this case is the opposite of negative 2 over 2 times negative 1/2. That's going to be 2 over negative 1 or negative 2. To find the y value of my vertex, let's plug that negative 2 back into the original function. So negative 1/2 times negative 2 squared minus 2 times negative 2 plus 6, which is a negative half times 4, or negative 2, plus 4 plus 6. Negative 2 plus 4 is 2, plus 6 is 8. This tells me that my vertex is negative 2, 8. Let's next find the x and y intercepts. That will help when we go to sketch a graph. The x and y intercepts, well, if we remember back to intercepts, to find x-intercepts, we're going to let y equal 0. To find y-intercepts, let's let x be 0. Maybe I'll find my y-intercept first. If I plug 0 into this function, well, in this form, it's actually pretty easy to figure out my y-intercept. If I plug in 0, this term's gone, and f of 0 is 6. So 0, 6 is my y-intercept. To find my x-intercept, I want to let y, or f of x, be 0. So this is a little more work. I need to solve this equation. Solving quadratic equations we did review in Chapter 1. I can solve it a few different ways. I could complete the square, I could use my quadratic formula, or maybe I could factor. I think what I'm going to try first is multiplying both sides by 2 just to get rid of this fraction. Maybe I'll even do it by negative 2 so that I have a coefficient of 1 on x squared, and that way we'll be able to tell if it factors. So if I multiply both sides by negative 2, this is still 0. This is x squared plus 4x minus 12. Again, that was to multiply by negative 2 on both sides here. And actually, I think this guy does factor if I think of a positive 6 and a negative 2. X plus 6 equals 0 gives me one of my solutions, and x minus 2 equal to 0 gives me my other solution. Like I said, you could use a quadratic formula here or complete the square as well, but this is probably the most straightforward solution. This tells me I have two x-intercepts, negative 6, 0, and 2, 0. This idea of having two x-intercepts should be familiar if we think about what a parabola looks like. It certainly makes sense that we could have two places where it crosses our x-axis. I'm going to actually clear some space here so I can sketch a nice graph. I've circled the 4 points that we have, our intercepts and our vertex. My vertex is over here at -2, 8. At 0, 6, I've got a y-intercept. At -6, 0, a horizontal intercept, and at 2, 0, I've got my other horizontal intercept. This should create a parabola that opens down, and that totally makes sense with a negative coefficient here. We need to keep practicing this, so let's keep doing it. Let's express the function in standard form first. So I'm going to find that vertex using -b/2a. I could complete the square, but I think this will be faster. -b/2a is -12/2 times 6. -12/12 is going to be -1. And to find the y value of my vertex, I'm going to plug that in. F of -1 is 6 times -1 squared, so 6 times 1, plus 12 times -1, minus 5. 6 minus 12 is -6, minus 5 is -11. So let me just keep track of this over here. Our vertex is -1, -11. We'll use that later when we graph. Knowing my vertex and knowing my value of a, I can write this in the form a times x minus h squared plus k by just filling in 6 for a, x minus a -1 or x plus 1, and minus 11. That's my k value. Again, this will give me a shift to the left 1 and down 11 to get that vertex to -1, -11. Okay, for part B, I want to find my x and y intercepts. My y-intercept is easy if I just plug 0 in. 6 times 0 plus 12 times 0, all that's gone. It's -5. So I've got an intercept, a y-intercept of 0, -5. Again, I'm going to keep track of that up here so we can clear space and graph in a minute. My x-intercept, I'm going to find by letting y be 0. Let me show you another way we might go about finding this x-intercept. I could set my vertex or standard form equal to 0. This might actually be easier to solve. It's kind of like we've already completed the square. If I add 11 to the other side and divide by 6, it looks like this. And now if I take square roots on both sides, I get positive or negative square root of 11 over 6 equals x plus 1. That's going to be -1 plus or minus root 11 over 6 equals x. Now these are going to be a little bit harder to graph. We might want to get a decimal approximation in order to do that. But I do still have two solutions, two values for x for these x-intercepts. This gives me an x-intercept at -1 plus root 11 over 6, 0. And another one at -1 minus root 11 over 6, 0. So again, maybe in order to actually graph those points, we might get a decimal approximation or look at that a little bit more carefully. I can tell you these values are about 0.354 and -2.35. So this will be a little more useful as we go to actually graph it. Let me just clear the screen so that we can graph this. My vertex is at -1, -11. My y-intercept is at 0, -5. So there was -5, and here's a point. I think I'm also going to try to approximately plot these x-intercepts. Remember, one was at about 0.3540, so that's quite skinny. It's going to be in here somewhere. And the other was about -2.3, so somewhere in here. This is going to work a lot nicer if you've got graph paper. But I think my parabola is going to look something like that. Okay. Let's wrap this up with a couple of application problems involving quadratic functions. Let x be the amount that airport shuttle fares increased, and r of x equals the revenue from each trip in dollars. So we're given the function r of x equals -4x squared plus 8x plus 60. How much should the fare be increased, so that would be an x value, to maximize revenue, our y value, what is the maximum revenue from each trip? Anytime I see this word maximize or perhaps minimize in another example, when I know that I have a quadratic function, and in fact I even know that because my coefficient on x squared is negative, this opens down, maximizing makes me think vertex. The vertex has two coordinates, it's a point, so we've got an x value and an r of x value from my vertex. It's asking me how much the fare should be increased. That corresponds to, well, the x value of my vertex. Then it also asks what is the maximum revenue, so there's that word maximum again, and revenue is the r of x or the y value of my vertex. So I think these two questions are just going to be answered with the two values of the vertex. So let's find our vertex, and the fastest way when I'm given it in the form ax squared plus bx plus c is to calculate negative b over 2a and then f of negative b over 2a, or in this case r of negative b over 2a. So let's do it. Negative b over 2a is negative 8 over 2 times negative 4. Negative 8 over negative 8 is just 1. I would say we already have the answer to the first part of this. How much should the fare be increased to maximize revenue? Well, I'd say increase the fare by $1. This is the x coordinate of my vertex. Let's plug it into 1 to find the corresponding y value. That'll be negative 4 times 1 squared plus 8 times 1 plus 60. Negative 4 plus 8 is 4, plus 60 is 64. If we increase the fare by $1, the maximum revenue will be $64. Okay, so using that vertex to get some important information in an application. It says it has 140 feet of fencing to fence in a rectangular vegetable garden. Find a function for the area of the garden she can fence, and then we'll find the dimensions of the largest area. So this looks like a pretty straightforward plan. If we can express this area as a quadratic function, then finding the largest area is just a matter of taking a look at and analyzing the vertex. Let me just review with you, this is in your textbook, but we've talked about modeling with equations. Now we're going to up that a little bit and look at modeling with functions. So here are some steps to follow. We'll express the model in words, we'll choose a variable, set up the model or write our function, and then use that model. In our case, we'll use it to find that largest possible area. This is what I'm going to roughly follow, and you should too in these examples where you have to write your own function. Let's go back here. First, let's express the model in words. So I'm working on part A just to write the model. Here would be one way to do that. I want an area, and this is just a rectangle, right? Rectangular garden. Area is length times width. So here's in words what model I want to use. Looking again at our next step, we need to choose a variable, identify all the variables that are used to express the function, and assign a variable to one quantity, express the other in terms of that symbol. We don't want to write a function of several variables, we just want one variable, so that'll be the trick to this. We need to express length and width both in terms of one variable. Well, the relationship that I have between length and width is really just related to this 140 feet of fencing. That's 140 feet to go all the way around or to cover the perimeter of this rectangle. If we think about what we know about perimeter, well, perimeter is 2 times the length plus 2 times the width. And in fact, in this case, I know the perimeter, so I can put that in here. 140. If I'm going to use just a single variable and write this as a function of one variable, I could use this to either express length in terms of width or width in terms of length. I think I could do it either way. Why don't we solve this for length to represent length in terms of width? Let me use a couple of intermediate variables here then. If L is length, and W is width. If I solve this for L, it's 140 minus 2W, and then divide by 2, so that would be 70 minus W equals L. All right. That way I can express length in terms of width. So if W is width, 70 minus W is my length. Moving on to my next step. Now I think I'm ready to do step 3, set up the model. We've got all our quantities represented in terms of the same variable. Let's go back and write our function. How about A of W for area, because we're going to express everything in terms of W. And my area function is length, 70 minus W, times width, W. And yes, indeed, this is a quadratic function. If I distribute that W, I could rewrite this as negative W squared plus 70W. All right, we've got part A complete. We're ready to answer the question in part B. We want to find the dimensions, and so dimensions, that's length and width, of the largest area she can fence. So that made me think of my vertex. Let's calculate negative b over 2a to start with and see what that means. This is negative 70 over 2 times negative 1. So that's going to be 35. And 35 is the input value, or the first coordinate of my vertex. So this is my width in feet, right? So the largest area she can fence, I already know, is going to be 35 feet wide. If I plug 35 back in and find the y value of my vertex, that's going to give me the actual area. Although I'm not sure that's even what's asked for. We don't even need the area. We just want to know what the dimensions are. The other quantity I really want to find is length. But remember that length was 70 minus W. So if I know that the width is 35, I think we can just use this to find the length. Turns out that this is going to be a square. That doesn't make sense. All right, 35 feet long, that sounds better, and 35 feet wide. Those are the dimensions of the largest area. We could find what that largest area is by plugging these in to my function A, but it's not necessary. It's not asked for.